Hello, my name is Ide, and I'm working on the Line platform development team, developing messaging functions and managing storage. Today, I would like to introduce how ID generation is done in messaging applications. First of all, I would like to briefly introduce our messaging app, which is the subject of this presentation. The messaging app currently has about 200 million active users, and about 4 billion messages are being exchanged through these users per day. Since it is hard to imagine how messages are actually sent, I have drawn a simple diagram of the Line system. Line's application is based on a very orthodox client-server model. When a user sends a message, the message sends to the backend server, and the backend delivers the message to the destination. When the client receives the message, it notifies the sender via the backend that it has read the message. Since there are 4 billion messages per day, so about 40,000 to 50,000 messages per second are exchanged in this flow. Now, about these messages. In order to identify each other, an ID called message ID is assigned to each message. There are various ways to format and assign this ID, but we use a globally unique and monotonically increasing ID. We use a globally unique and monotonically increasing ID, which is numbered by the backend server. The timing of ID generation is when a messaging is sent by the sender, the backend assigns an ID and delivers it into the recipient and to the sender. So the question of how to generate this ID, the requirements for the ID generator are that it must not become a bottleneck for messaging, that it must be fast enough, that it must be also simple as a C code on the right-hand side, and that it must have a low maintenance cost. We decided to implement the ID generator utilizing Redis in order to meet these requirements. And also because we have already managed many Redis clusters, we are going to implement this. When trying to use Redis for ID generation, I think the simplest setup is to use a single Redis master replica pair, which is fast enough for ID generation. In fact, it gave us the performance we needed for a backend. However, after a few years operation, we realized something. In this setup, is it reliable? Is it available when there is a problem? And is it scalable? So these are some of the problems. To see if these questions really matter, we have conducted an experiment. The first case is when the Redis host suddenly dies. This is a common problem for us who run thousands of Redis instance clusters. And in this case, if only the master dies, the simple solution may be to fall back to the replica. However, what we need to be aware of is this Redis platform's replication conducted asynchronously. If Redis dies before replication completes, no one will know what the last ID generated was. And what if both the master and replica dies? We don't even know how to recover them in the first place. If you mistakenly restart ID numbering from the previously generated ID, you would have duplicate IDs, which will further delay the recovery. Since users cannot talk to each other during the recovery process, it is absolutely necessary to avoid this problem as a server operation point of view. The second case is one of the most common failures in application, which is service across multiple networks. If the network between the master replica and the backend is broken, ID generation cannot be performed, and eventually messages cannot be sent. The solution is to wait for the network partition to be resolved. But we don't know if this partition will be instantaneously recovered, like take 1 second, or it will be resolved in 10 minutes, or even a day. As it will block users from talking until it is resolved, this is another problem we want to avoid. So, how can we improve the situation? Let's take a look at the requirements. First of all, it should be a globally unique and monotonically increasing ID. So that's one requirement. Since various features are depending on the functions such as message, read feature, sequencing, and storage optimization, it is not realistic to change now. Also, the ID generator needs to be scalable in order to resist network partitioning and hardware failure. Also, since the message ID is already used in the API and schema, we need to make changes without breaking changes. Finally, if we don't think about breaking changes, we can consider other formats such as UUID or GUID. After a lot of experimentation and research to find a scalable way to generate globally unique and monotonically increasing IDs with 64-bit integers, we came to a conclusion to use Snowflake ID format used by Twitter as tweet ID. In ID format called Snowflake, this consists of 3 components. The timestamp is a field that is updated every 1 millisecond and provides a property that the ID is monotonically incremented in this field. Work ID is used to determine which machine generated this ID, and the sequence is used to make it unique among IDs generated within the same timestamp and the same worker ID. We thought about adapting the Snowflake to our system as is, but we decided to use it with a slightly different format. We decided to name this ID and ID generator as MIG. So there are 2 differences between the MIG ID format and the Snowflake one. Well, the first is that we changed the resolution of timestamp from 1 millisecond to 10 millisecond. This means that the timestamp would only change every 10 milliseconds. Originally, it could only be used up to 69 years, but reducing the resolution, it can now be used up to 200 years. The sequence was increased from 12 bits to 18 bits, so that the number of IDs a worker can generate in 10 milliseconds can be increased to cope with the sudden increase in messages. It may be difficult to imagine in your mind whether this form of ID generator would work as it were told. So therefore, we will show you how it works in the next page. Unlike the previous setup, with a single Redis master replica, MIGs can now load balance by having multiple MIG lineup. Each MIG can create an ID by combining the current timestamp, its own work ID, and sequence whenever a request comes in and return it to the backend. Since the timestamp of each ID differs depending on the time at which it was generated, we can guarantee that the IDs will increase monotonically when compared with each other if the clocks are synchronized between all hosts. In addition, if some hosts die, other instances can continue to take over this creation. And since the state is not shared among hosts, we can easily add more hosts. In addition, the ID generator that was only in one data center can now be easily deployed in multiple data centers. This solves the problem of scalability and availability that I mentioned earlier. Very happy. Thus, I thought that the MIG would solve everything. However, the story was not that simple. Yes, the introduction of MIG has led to duplicate IDs in the client backend and has broken the assumption that IDs always increase monotonically. Today, I would like to introduce two cases that were discovered during this test. The first issue is that the ID does not monotonically increase. In fact, the timestamp-based ID has a problem that it cannot monotonically increase if there is a leap second or NTP time adjustment. In this example, a clock drift occurs between the second and the third IDs, causing the clock to go back about 5 seconds. In this case, we can see as a result of the clock drift, the ID is indeed no longer monotonically incremented. So now, how would we be able to fix this problem? This case can be worked around in a way that is well known in the Network Time Protocol NTP server. The problem is that when a clock drift occurs, the actual timestamp in the gray line is suddenly changed to a modified timestamp in the blue line, which is then followed. And this is the issue. So therefore, I took the method of gradually modifying the timestamp to the correct one as shown in the orange line, like the slew mode used in the NTP server. This allows us to modify the timestamp without breaking the rules. Well, that the ID will eventually increase to monotonic. The next problem is the problem occurred in our backend storage. We are using multiple Redis clusters as a storage in addition to HBase and other storage. And multiple commands are bundled in Atomic and rely heavily on the Lua script feature of Redis to reduce the round-trip time required to process the commands. The function of Lua script in Redis is to write multiple get commands in a Lua script and execute them as a single Redis command. In this sample script, the last message ID of the user ID is retrieved, and the message object stored in Redis is retrieved using that ID. So if you write a raw script to implement this command in a single eval command, it will look like this. At first glance, this raw script seems to work well, but when I tried to run it, something was wrong. The above two gets actually returned an object, but the actual raw script did not. In other words, the message was not found. In this sample, messages were lost, but in the actual phenomenon, data related to IDs were randomly lost, and data related to IDs were duplicated. So it took a lot of time to do the investigation. After investigating the cause of the problem, I realized that if I convert the data like a taunt number inside the Lua script, I get a completely different result. Yes, the Lua language, especially the version of Lua that is built into Redis, also utilizing floating point numbers to represent integer. So it cannot correctly represent the IDs generated by MIG. Since Lua 5.5 version, integer types have been introduced, which will solve this problem. However, I am still using the old version because there is no compatibility between versions. I won't go into the details of the solution as it would take too much time, but it was quite a challenge. The script I introduced here is very simple and could have been solved by handwriting. But in reality, I tried to implement big int in Lua script or to compare values directly without converting them to numbers. In fact, I tried to avoid data conversion in the Lua world on a case-by-case basis by implementing big int in a Lua script or trying to compare values directly without converting them to numbers. There are many more interesting issues to discuss, but that's all I have to say for now. For the past 10 years, Line has been focusing on the technology of distributed system to ensure the reliability of the live Line platform. In the next 10 years, we're working to develop a more reliable system that will allow us to expand that distributed system beyond the limitation of the data center level. In this session, I introduce how we are implementing the ID generator as one of them. By converting to timestamp-based IDs, we are able to get a fast, multi-data center level, scalable ID generator. I also introduced some bugs that I found while migrating. This time, I talked about clock drift and floating point number representation, but if you are introducing a new feature to your service, it would be a good idea to carefully check the internal implementation of the client as well as the server. You may find bugs and specifications that you did not notice when you implemented it. This concludes my presentation. Thank you very much.